first flipped classroom lesson. Now, as you remember we discussed in class, we're going to be looking at the mini topic of refraction and its applications by this sort of flipped classroom approach. So we'll be watching the videos for homework and then doing discussions, questions, and experiments when we're in class. Okay, so today, what is refraction and how does it happen? The basic introduction. More detail to come in further videos. Alright, so refraction is just basically the way that light bends as it passes between two different optical media. So what are optical media, I hear you ask? Well, an optical medium is anything light can pass through easily. So we would consider air, vacuum, glass, water, plastic, and so forth to be examples of optical media. Now, here down the bottom we have a fairly common example of refraction in action. It's one of these demonstrations we use a lot in junior science classes. So we have a pencil that's been put into a beaker full of water, and we can see when we look at the top that the pencil appears to be bent. So what's happening is the part of the pencil that's in the water, when the light rays come off that part of the pencil, they are refracted or bent as they pass from the water back into the air. And it's that bending that causes the optical illusion we see when we look at it like that. So a bit later on in this video, we'll try and explain exactly why that happens. Now, this whole bending of light thing, at the core of it, it really depends on how the speed of light is different in different materials. So we'll start off by having a little refresher about the speed of light and its value. Okay, so hopefully you remember that nothing in the universe can travel faster than the speed of light in a vacuum. So what's a vacuum? It's just basically outer space. So the speed of light in a vacuum is like the universal speed limit. You can't go any faster than that. Now we use that speed of light in a vacuum all the time in physics. So we've given it its own symbol. We've given it the symbol lowercase c to represent the speed of light. And what is c? Well, it's about 3 times 10 to the power of 8 meters per second. Technically, it's more like 2.9978 times 10 to the power of 8. But for most purposes, we can just round it to one significant figure and call it 3. Now, to get a handle of exactly how big that is, it's a pretty high speed. 300,000 kilometers per second, basically. And it's one of those numbers that's so big, it's hard to really wrap your head around. I like to think of it like this. If I could make light travel in circles, which it can't, but if I could, 3 times 10 to the power of 8 meters per second is about 8 times around the equator of the Earth in 1 second, so pretty fast. Now, speed of light in other materials will be slower. So for example, in water, it's about 2 times 10 to the power of 8, but still quite quick. And then here we've got a little table that shows the speed of light in a number of different materials. So you'll see for vacuum and air, it's 3 times 10 to the power of 8 for both. In reality, light is a little bit slower in air, but it's so close that when you take it to 3 significant figures like we've got here, you don't observe any difference. And then as we go down through progressively thicker materials or denser materials, we'll see that the speed of light drops off. So glass is the densest material, therefore it has the lowest speed of light. Now, one concept that's useful when talking about the speed of light, and we'll be using this idea a fair bit in this topic on refraction, is something that we call the refractive index, little n of a medium. So little n is the ratio of the speed of light in a vacuum that we've already called c to the speed of light in that particular medium. Now, to make sure we don't get confused between the speed of light in a vacuum and just say the speed of light in something like water or glass, we've given it its own symbol. We've used the letter lowercase v to represent the speed of light in that particular material. And you'll see in the top right-hand corner here that the refractive index is equal to c divided by v. It's the ratio of the two speeds to each other. Now, because v will always be less than or equal to the speed of light in a vacuum, that means that n will always be greater than or equal to 1. So for example, if we were calculating the refractive index of something like water, well, the speed of light in water, v, will be smaller than the speed of light in a vacuum. So that when we do c divided by v, we're going to get an answer that's bigger than 1. And that's always going to be the case. The only time you'll see light being refractive index being equal to 1 is if you're working with something like air or vacuum, where the speed of light in that material is the speed of light in the vacuum c. So the refractive index will always be greater than or equal to 1. And refractive indices do not have SI units of measurement. So we don't write down a unit when we write down a refractive index. Reason for that being is it's just a ratio of one thing to another. And you might remember from maths that ratios are always unitless. So when you write down the refractive index, just write down the number. Don't bother about putting a unit afterwards. Okay, so here's my table again, and this time I've put in, as well as the speeds, I put in the refractive indices for each material. So you'll see that air and vacuum both have a refractive index of 1. And then as we go down the table, as the speed of light in that material gets smaller, the refractive index will get larger. So glass has the slowest speed of light, and therefore the highest refractive index of all of those materials we've listed. Okay, so a quick example calculation. How would we find the refractive index of whale oil? And this is a real thing, I found it in a textbook. If we know that the speed of light in whale oil is 2.05 times 10 to the power of 8. Well, the first thing we'd do would be to write down all of the information we know about this. It's a good first step for solving any sort of physics problem. And when I write them down using the correct symbols rather than words. So I've got here the speed of light in whale oil, V, equals 2.05 times 10 to the power of 8. C equals 3 times 10 to the power of 8. And then as my last little bit of my introductory line, I've written down what I'm trying to find. So I'm trying to find the refractive index N. From there, chuck in the formula, N equals C divided by V. Insert the values for C and V, and then solve. So we can see that for whale oil, the refractive index, N equals 1.46. Okay, pretty straightforward calculation. And you could take that formula, N equals C divided by V, and rearrange it to make V the subject if you knew the refractive index and you wanted to find the speed of light instead. Pretty simple, we won't look at that particular example. Okay, so now getting back to refraction. Refraction, or that bending of light, only occurs at the boundary between the two different media you're working with. So the light will bend, but it'll only bend at that point where it hits the boundary between the two. Light will travel in straight lines otherwise. So what you're going to see is you're going to see two straight lines, and there's going to be a kink where it hits the boundary and bends. Now that will only happen if the light hits the boundary at an angle. If it hits it at exactly 90 degrees, like head on, it will just pass straight through and won't be bent or refracted in any sort of way. So for example here, we have a little diagram showing a beam of light passing from air into glass, and that beam of light is hitting the glass at exactly 90 degrees, so it's just passing straight through without being bent at all. So that's pretty boring. If the light is hitting the boundary at an angle, then we need to describe exactly what angles it's hitting at and what angles it's passing through at. So we need these two concepts, the angle of incidence and the angle of refraction, to describe how the light bends. Now we're going to measure both of those angles around a normal line. So a normal line is like a little 90-degree dotted line at the point where the light ray hits the boundary between the two different materials. And for angle of incidence and angle of refraction, we use the symbol theta, which we always use for angles in maths or physics. We use a lowercase I to represent the angle of incidence and a lowercase r to represent the angle of refraction. Be very careful when working with these sorts of problems that you don't mix up your indices. So here we've got a little diagram of light passing from one material into another and the light ray being refracted or bent as it passes through. And I've marked on there where you'd measure the angle of incidence from and where you'd measure the angle of reflection from. And you can see that they're both measured around the normal line, which is that little dotted line that hits the boundary between the two materials at right angles. Okay, so our first example here would be refraction inwards. So whether light is refracted inwards or outwards depends on the refractive indices of the two materials and how they compare to each other. So light will be bent inwards when it goes from a material with a lower refractive index to a material with a higher refractive index. So for example here, we're going from air into water. Now we know that air has a refractive index of 1 and water has a refractive index of about 1.33. So we're going from lower into higher. When that occurs, the light ray will be bent inwards. So we've got a little simulation here. We can see that as we move the light ray backwards and forwards, there's a faint portion of the light that's reflected. That's that little faint red thing. But most of the light is refracted through, and as it is refracted through, it's bent inwards. So if I get my protractor here, and place it at the point where it passes through from air into water, and place the laser at 30 degrees for the angle of incidence, you can see that the angle of refraction is less. It's about just under 25 degrees. So that brings us to our next point. When light's being refracted inwards, the incident angle will always be greater than the refractive angle. So here, incident angle is 30, refracted angle is about 24, so the incident angle is the larger of the two angles. On the other hand, we might be dealing with light refracted outwards, and that occurs when you're going from a higher refractive index to a lower one. So for example here, we're going from glass, which has a refractive index of about 1.5, to air, which has a refractive index of about 1. So we're going from higher to lower. Now we'll show a quick demonstration here. You'll notice that as I move this backwards and forwards, at certain angles the light does not refract through at all. It just reflects off the boundary and heads back into the glass. Now there is a reason for that. It's not a problem with the simulation. There's an actual physical reason for that. We will discuss that in a later video. It's called total internal reflection. Now you'll see here, if I put the laser, so the angle of incidence is 30 degrees, then the angle of refraction this time is larger. It's about 46 degrees, I'd say. That'd be my estimate. So when your light's refracted outwards, the incident angle will be less than the refracted angle. So here we've got an incident angle of 30 and a refracted angle of about 46. So the incident angle is the smaller of the two angles. It's a key point to remember. So now that we know this, let's have a quick look at trying to explain that little magic pencil illusion we saw at the start. So what's happening here is the rays of light from the part of the pencil that's immersed in water, as those rays of light pass out of the water and into the air, because they're going from a higher refractive index to a lower one, they will be bent outwards. Now when they're bent outwards and they're picked up by our eye is assuming that the light has traveled in straight lines to get to it. Because that's how things normally work. Light rays travel in straight lines. So our eye projects those rays backwards, and to our eyes, it appears as though the end of the pencil is at the position Y in that diagram there. And that will occur all the way along the length of the pencil where it's in the water. So that's how we get that little kink. So it's caused by the light rays passing through the water and refracting outwards as they enter the air. That's what causes the optical illusion. Okay, so that completes a brief little introductory video on refraction. Next time we're going to look at a thing called Snell's law, which is an attempt to mathematically describe this whole refraction business. So we know a few points now. We know that light refracts inwards as it goes from a lower to a higher index, and refracts outwards as it goes from a higher index to a lower index. But suppose we wanted to work out those exact angles. So suppose we wanted to work out the exact angle of incidence and the exact angle of refraction for light passing between two particular mediums. If we want to do that, we need to use a thing called Snell's law. So we'll be looking at that in our next video. Okay, until then, see you later.